So, boys and girls, we have question 7a. We are given figure 7 show the interference pattern from a double slit experiment. We want to determine the distance between the central bright and the third dark fringe if the two light sources are in phase. So the question asks us to find the distance from the central bright to the third dark fringe. So if we refer to the list of equations given, we know that we are going to use equation 72. Okay, 72 ym, whereby ym represents the distance of the n dark fringe from the central bright. So we write down the equation first. So we are going to use ym equal to m plus half lambda d over d. So m is the order number starting from 0, 1, 2, 3, 4, 5, and so forth. So we want to find the third dark fringe. So the third dark fringe will be corresponding to order numbers of how much? So we can count. So start from 0 is the first dark fringe. This is second dark fringe, third dark fringe, fourth dark fringe. So we can see obviously our third dark fringe, the order number m is equal to 2. So we write down first our m will be equal to 2. Anyhow, in order to solve this question, we need to know the value of lambda d over d. So how we are going to get lambda d over d from the interference pattern given? So we understood that the distance between two adjacent fringe, these two adjacent dark fringe, is what we call fringe separation, delta y, whereby delta y is lambda d over d. See, lambda d over d. So this lambda d over d in this equation can be represented by delta y. So here to here is another delta y. Then from this dark fringe to the next adjacent dark fringe is equal to delta y. So from this dark fringe to another adjacent dark fringe is delta y. So we can see obviously 4 delta y is equal to 22 cm. Okay, so from that I can calculate my delta y. Delta y will be 22 over 4. So it will be 5.5 centimeter, or is equivalent to 5.5 to the power of negative 2 meter. Okay, so once I get the delta y, so we understood lambda d over d, if we refer to equation 73, so it will be equivalent to delta y. So we have m plus half delta y. So then I put in the value. So the third dark fringe, the order number is 2. So the delta y is 5.5 to the power of negative 2 meter. So I'll get the distance between the central bright and the third dark fringe will be 0.14 meter. Then I solve question 7a. So class 7b, we are given a 666 nanometer light illuminate on a 2500 line per centimeter diffraction grating. Then we observe 13 bright fringes on screen. So we observe 13 bright fringes on screen. Then we know that for the diffractions pattern, the center, we must have a central bright. And then on the either side of central bright, we are going to form a series of bright dots. Okay, so question 1, we want to calculate the maximum diffraction angle of the bright fringe. So we want to find what is the maximum diffraction angle, theta maximum, that we can get for these questions. So in order to calculate the maximum diffraction angle, we are going to use equation 78. So we have d sine theta equal to n lambda. So our sine theta is proportional to the order number. So it will be understood that in order to find the maximum diffraction angle, the order number will be maximum. Okay, the order number that we substitute must be maximum. So in order to solve this question, we have to determine the grating spacing, the maximum order number for this question, and the wavelength is already given 666 nanometer. So I can calculate the grating spacing first using equation 79. So I put it aside, I calculate the diffraction grating spacing. So I have d is 1 over n. So 1 over the grating have 2,500 lines per cm. Okay, so 1 over 2,500. So I'm going to get 4 to the power of negative 4 centimeter. Then I have to change it to SI unit meter. So I have 4 to the power of negative 6 meter. So I have to determine the maximum order number that's corresponding to the maximum diffraction angle. So in this question, we are going to observe 13 bright fringe, and we understood beside the central bright, we are going to form a series of bright fringe on either side of the central bright. So it means that 2n, 2 multiplied the maximum order, plus with 1 will equal to 13, because we observe 13 bright fringe. So when we do our calculations, the maximum order number will be 13 minus 1 divided by 2. I'm going to get 6. Okay, so this is n equal to 1, 2, 3, 4, 5, 6. It happened on either side. So here is 1, 2, 3, 4, 5, 6. Yes. So the maximum order is equal to 6. And then we put it here lah. So our grating spacing is 4 to the power of negative 6 sine theta maximum equal to 6 times lambda is 666 to the power of negative 9. So I determine the sine theta and then I shift sine. I will get the maximum diffraction angle will be around 87.44 degree. Okay, then we done question 1. Question 2. Does the separation between the two consecutive bright fringes decreases, remain unchanged, or increase when a grating with a larger number of lines per cm is used? So if we use a greater n, will the separation between the fringes, the separation between the two fringes will be decreased, unchanged, or increased? So in order to solve this question, I will try to relate the angle, the diffraction angle with the n. So refer to equation 78, d sine theta equal to n lambda. So d is 1 over n, so sine theta equal to n lambda. So the diffraction angle will be n lambda. So from the equation, we can see obviously the sine theta, the diffraction angle, is proportional to the numbers of lines per unit length for the grating. So greater the numbers of lines per unit length of the grating used, greater is the diffraction angle. So it means that when the n is larger, See, we use a grating with larger number of line per cm. When n larger, so the diffraction angle will become greater. So when diffraction angle become greater, it will means that the separation between two consecutive bright fringe increases. Okay, so this one will be our answer.